or okay, so.
Yeah, so, well, thank you very much for having me. I'm very new to the IPHT. I arrived just 4 years ago. But the more time I spend here, the more I realize that this is a truly unique place. I mean, there are many labs that will promise you that you can get there and do nothing but research. But then you see all our colleagues at CERN or American National Labs spending half their life in committees. While here, instead, it's really true that we have the luxury of only doing research. And the only other place I know like this in the world is the Institute for Advanced Study. And I'm saying this for two reasons. So it's true, but that was kind of arahiri. I mean, like I did it to myself. No one forced me. Yeah, no, I'm saying this for two reasons. One is that we have no excuse not to do research at the same level at IAS. And the second one is to say that I'm not at all qualified to talk about the past. So I will mostly talk about the present of our field. Then I will immediately contradict myself and also say something about the past, but it will be just an excuse to jump into the future. So most of the talk will be about the future. But well, let's start in the present. So today we have a theory of fundamental interactions that can describe essentially all phenomena from the CMB, so almost the size of the universe, all the way down to the smallest distances that we can probe. And this is really a huge range. So it's about going from 10 to the 28 centimeters all the way down to 10 to the minus 17 centimeters. And what's even better is that we can do it with a handful of particles, so just about 20, and in a relatively compact way. So we can write all the, what's going on? Yeah, so we can write all the laws that describe natural phenomena in 3 lines, essentially. Of course, this is a lie, because to unpack these 3 lines and actually make the predictions that I advertised above, you need thousands of pages of calculations, but still, it's quite remarkable that we've reached such a level of understanding, especially if you then compare our most precise theory predictions, which are better than a part in a billion, to the most precise experimental determinations that correspond to them, which are also better than a part in a billion. And we have numerous results that show this incredible level of agreement. Now, well, here comes the moment where I contradict myself, because I want to take a step back and go to the time when IPHT was born. So it's quite impressive to see what the picture was at the time compared to what it is today. So at the time, we essentially had no idea of this old theory. We had discovered a few of the particles that made up the picture, but we didn't really have a unified theoretical framework to understand what was going on. And well, in the rest of these slides, you're going to see these white circles for particles that have been discovered, and these black circles for particles that were just hypothesized. And so you see, at the time that IPHT was born, we didn't know that much. But even just 5 years later, the picture was quite different. So we had, yes?
How did we know that the neutrino existed?
Which neutrino? Of the, wait. Oh, yeah, the electron neutrino. Yeah, so well, actually, yeah, that's a good question. So we knew it, so that's why I didn't want to do too much research.
In 1960, so IPhT6, and the new had been discovered 1 year before in 1960.
Yeah, no, but I think that he wanted to know exactly how experimentally. So I think it was coming from decays, mostly in cosmic rays, so you could see the missing energy coming out of the decay. But yeah, so, but if you make a small step forward of just 5 years, the table was starting to being filled up. So we already hypothesized the vast majority of the particles we know today to exist, and we had even discovered a few of them. And if you take a step forward of another 10 years, then I would say the picture was almost complete. We had already observed a bunch of these particles and hypothesized all the remaining ones. Then it took another few years to discover the W and the Z. And for the last three pieces of the puzzle, so the top quark, the Higgs boson, and the tau neutrino, it took a much, much longer time. So about 17 years to discover the top and the tau neutrino, and another 12 years to discover the Higgs. So, well, you can draw several conclusions from this progression. So the first one is that, of course, presented as it is, it's a complete lie, in the sense that the past was not a long walk of success. I mean, throughout these decades, we were confused. People didn't know what was the right theory. It's not that they immediately theorized the correct particles and just went for them. There were a lot of mistakes being made, thousands of models that had nothing to do with nature being proposed. And actually, I found interesting to compare the accounts of the past that were given by people that did not live in the past, like me and Brando, to the accounts of the past that were given by people that were there, which were reflecting much more all this confusion. And this makes me feel a lot better about the present, because we're often tempted to think that the past was much better. Look at all these glorious discoveries in just of the span of a few years, while we are here suffering and not really understanding what's going on. But I think that this feeling is pretty scale invariant. I mean, I don't think it was very different back then. And the second thing that you can try to deduce from this picture is what's coming next. So as I said, I've shown this very short history on which I'm not at all an expert, as the question I almost couldn't answer shows you. So I showed it as an excuse to think about the future. So the reason why our knowledge improved so dramatically over the years is that we moved up in energy as we were moving forward in time. And we roughly explored a factor of 220 in energy from 1971 up to today. And so, well, one natural question to ask is whether all that we learned in the past is also telling us something about the future. So what's coming up next? So today we are at some energy scale, and we want to know whether the next 10 years, 20 years, 60 years hold as much fundamental physics as the past 60 years were holding. And well, it's not an accident that the Higgs boson is at the center of this picture of elementary particles. The reason is that it's giving mass to everyone else, essentially, except for the particles that do not have a mass. So the energy scale of what we today call the standard model of particle physics is essentially fixed by the Higgs mass squared. So today we live somewhere here at a scale determined by the Higgs mass, and we want to know what happens next. And well, we can start by assuming that nothing happens for a long time, so that we keep exploring higher and higher energies, and we see nothing up to some much higher energy scale that I'm calling lambda UV. If this is the case, well, we can make a simple prediction for, or maybe post-diction for what we observe today, essentially based on dimensional analysis, or if you want to be fancier, on the selection rules of dilations. So dilations are broken, but their selection rules still make a prediction. So if really there is nothing up to some large scale, you expect all the operators in the standard model of dimension delta to come in the Lagrangian with a coefficient with the appropriate dimensions. So 4 minus delta, since we are in 4 space-time dimensions. And here I'm setting C and H slash to 1, so the C here is really an order 1 number. The problem, or maybe actually the interesting observation, is that the Higgs mass, which, as I just said, sets the scale for the whole standard model, is associated to an operator of dimension 2. So if you ask what's the natural expectation for what it should be, in this picture where there is nothing up to a large scale, it should be the large scale squared. So we made these, let's say, ansatz on what nature could look like, but we immediately found a contradiction. So we found that our theory prediction is much larger than what we observe experimentally. So this might sound like good news. It means that this picture where nothing happens for decades, probably it's wrong. What's even better is that if you think about the problem a little bit more, you will find that essentially any possible resolution of this apparent tension changes a lot the way we think about nature. The first option, which is probably the most conservative and the cleanest theoretically, is that there is some new symmetry. So this coefficient of order 1 that I glossed over could really be 0 naturally because of asymmetry, or much smaller than 1. However, well, if this is the case, you're immediately making a prediction for current and future experiments. So you're saying that at some scale not too far from the Higgs mass, you should see a bunch of new particles or some new dynamics realizing these symmetries. And the typical symmetries that can do the trick are supersymmetry or scale invariants. There are also some more speculative directions that we're thinking about right now, which is that the symmetry might be more subtle than the traditional ones. I'm sorry, yeah. It could be some non-invertible symmetry that is not as simple to describe as the ones that we've thought about so far, but this is very speculative. I mentioned it just because it's a nice example of cross-contamination at the lab, because we started thinking about it after I started talking with Pier Francesco, who's in statistical physics. So this is a good example of two fields that are very far away that are coming together. Maybe nothing will come out of it, but I'm mildly optimistic. The second option is that the picture is indeed what we drawn, so some I scale very separated from the Higgs mass, but there is a multiverse. What do I mean by there is a multiverse? So what I mean is that, again, when I wrote this order 1 number, I wasn't fully precise. In reality, if you have some theory at this scale where you can actually compute the Higgs mass, you will find that it's a sum of multiple contributions. And it's possible, for example, in the theories that Mariana was describing yesterday, that you have many different vacua where these different order 1 numbers change. Let's say you have 10 to the 500 vacua. You might easily find one where all these numbers, even if they're all order 1, they cancel each other to very high precision. And they explain why you see a scale that is so much smaller than the fundamental one. Interestingly, well, these many vacua could in principle actually be realized in nature. So if there is a long enough period of inflation at the beginning of the universe, you might populate all these vacua as disconnected patches in the universe. So these vacua are cosmologically long-lived, so you might start in one, then tunnel to another one at lower energy. The one at lower energy would like to eat up all the space-time, like in a normal phase transition when the water boils, eventually all the water boils. But during inflation, space-time is expanding exponentially. So the bubble walls of the lower energy vacuum never catch up to the whole space-time. And eventually, space-time fragments in many different bubbles that realize many different vacua. And an observer in the middle of this bubble might have to go hundreds of billions of light years away before seeing the boundary or before seeing another boundary. So effectively, an observer such as ourselves might just see a single universe and not be aware that this is what nature had in store for them. As you can see, I'm progressively going crazier in my explanations. Of course, in this story, I mean, it's not enough to postulate the existence of this multiverse. You also have to explain why you're in such an unlikely corner of this multiverse. So why do we see that particular patch where all these numbers cancel each other accidentally to be orders of magnitude smaller than they should be? And there are a few ways to explain it. One is creating models where all the universes that don't have a small Higgs mass crunch. Another one is to postulate the existence of observers just for the universes where the Higgs mass is small. Sorry, not to postulate, but I mean, there are ways to show that maybe observers arise only in these special universes. And finally, you can build models where actually a small Higgs mass dominates the multiverse. It's the most likely occurrence. But setting aside, let's say, these details, let me take one extra step towards craziness. So yet another thing that could explain why we see such a small scale for the standard model is that quantum field theory stops working at some point. I mean, to get this estimate, I made an assumption. I think it was a very honest assumption, which is that I can integrate out degrees of freedom a la Wilson. So essentially, I'm assuming that effective field theory is a good description of nature, which has always been. I mean, as I wrote here, you don't need to know the mass of the proton if you want to describe the trajectory of a ball that I'm throwing from the stage towards the audience. And I mean, this idea made precise in quantum field theory by the normalization group has had thousands of applications. Here I'm listing 4, but essentially it always works in our description of nature, and it has been very powerful for normalization, for understanding approximate symmetry from the fact that we're really looking at things from large distances, to precision calculations at colliders, but even gaining insight of quantum field theory by integrating out branes in string theory. So this assumption essentially always works, and so for it to be broken, something very dramatic has to happen. One concrete example is if high energies and low energies mix to some extent. One way to do it is, for example, if space-time is non-commutative. This is the only example I know where you can start with some high energy fundamental scale and generate an IR pole. Of course, well, these ideas break Lorentz symmetry at order 1, so they have nothing to do with our description of nature. And so you might just want to discard completely this option. And I wouldn't completely disagree with you. I just would like you to keep in mind that gravity likes to mix high and low energy. So in quantum mechanics, if you put a lot of energy in one point, you are exploring short distances. In general relativity, if you put a lot of energy in one point, you're making a big black hole. And if you want, this is the dumbest way why it's hard to combine general relativity and quantum mechanics. But it's also suggesting that maybe once you do it, there is not such a sharp separation between short distances and long distances as in ordinary quantum field theory. Anyway, so I don't want to convince you that one option is better than the others. I just wanted to list the option to show you that no matter what's the explanation, it's going to change quite a bit the way we think about nature. And theory is obviously pulling in one direction. So if you ask me what's the cleanest, best answer, I will immediately tell you that it's symmetry. Theoretically, the other two options are not even so well defined. I mean, we don't even have fully complete models that realize them from beginning to the end and make very precise predictions. However, well, here comes the slightly less pleasant part of our job, which is that at some point we have to go talk to our experimental colleagues. So I've seen a lot of wonderful mathematical physics talks that were so pristine and beautiful that really made me feel happy. But unfortunately, I am much closer to experiment, and so when I write a nice theory, then I ask my colleagues if it makes sense or not. And they would tell you that the symmetry idea, sure, I mean, it can still almost work, but not quite, because we've probed energies close to the Higgs boson mass in great detail, and we have not found any trace of these symmetries that I was talking about before. What's even worse is that there is another parameter in our description of nature that has the same tension as the Higgs mass, but much more dramatic, and it's the cosmological constant. The cosmological constant, roughly, it's at 0.1 millieV to the fourth. And so experimentally, actually, we probed much higher energies than the cosmological constant. So in this case, unless really missed something basic about theory, the symmetry explanations that I was describing before do not work at all. The only concrete explanation we have for the cosmological constant is this multiverse picture I was telling you about before. So if you want to summarize this talk in a single slide, we have two parameters in our description of nature today that are the most relevant, in the sense that they are associated to the most relevant operators. And they're also the most relevant in a more, let's say, loose sense, in the sense that since they're the most relevant in a precise sense, they're also the most relevant in our description of nature at low energies. So if you ask what these two parameters means for the way reality looks like, the cosmological constant essentially is telling you what's the maximal size of the observable universe. So not understanding its value amounts to saying that we don't understand why the universe is so big. theoretically, you would expect it to be much, much smaller, so small that observers like us would not exist. The Higgs mass, instead, is determining the range of the weak force, the masses of all elementary particles, so eventually, complex chemistry and life as we know it are very sensitive to its precise value. So we have these two parameters that, in some sense, are the most important for our description of nature, and we also don't understand them at all theoretically. The cosmological constant and the experiment are pulling us in one direction, and theory is pulling us in the opposite direction, so towards symmetry. And to conclude, I have no conclusion, but I'm sure that the future is going to be exciting. So I cannot put a precise timestamp on when we're going to solve these problems, but no matter what the solution is, it's going to change a lot the way we think about nature today. So thanks for your attention.
Thank you very much for this very, very nice talk. Is there any question?
While you showed this nice diagram of known particles, you forgot that there is one open question, which is about, for instance, there are several, but at least one is dark matter.
Yes.
Okay, and and there's supposed to be a large fraction of the universe in form of dark, assuming it's matter. Okay, it's not a modification of general relativity or something else. And certainly this should influence the picture. We cannot just say, I mean, I always read things where one has a feeling that dark matter, okay, we say there is dark matter, and then we forget about it.
Yes, so indeed. So yes, I forgot it kind of on purpose. So it was in the title of the talk, but then I realized I didn't have enough time to talk about it, but I'm glad you asked the question. So indeed, also the first picture, let's say, in the talk was kind of a lie, because we do know how to describe almost all phenomena in the observable universe, but not exactly all of them. And one is dark matter, and the other one is the actual size, so the cosmological constant. The reason why people often factorize the two problems is that dark matter can be explained easily with nothing radical. So imagine that you have a particle that's only gravitational coupled to us, and when the universe is reheated after inflation, it gets some amount of energy density. So the inflaton is decaying both to us and the dark sector. And further imagine that this particle has roughly weak interactions. Then this is a perfectly acceptable dark matter candidate that has no observable signature, essentially, modulo the gravitational one that we already observed, and doesn't change radically the way we think about particle physics. So in some sense, factorizes compared to these other two problems. On the other end, there are also examples where thinking about, say, the Higgs mass or the cosmological constant instead tells you something about dark matter. For example, if you marry the picture of, say, supersymmetry at this scale, then one of the supersymmetric particles would be a natural dark matter candidate. To some lesser extent, if you marry the picture of a multiverse coming from string theory, then you would generically predict axion-like particles from compactifying the extra dimensions, which are other natural dark matter candidates. So in some sense, in our experience, it's always gone the opposite way that you're suggesting. So we thought about the hierarchy problems, and then we found natural dark matter candidates. Rarely it was the opposite. There are some attempts to argue that maybe dark matter has a deeper connection to this problem than just being a byproduct of thinking about them. But it's always within one of those frameworks in some sense. So for example, if you're in a multiverse, you might try to argue that maybe the dark matter scale and energy density is also set by anthropic arguments, because there is this interesting numerological seesaw between the weak scale, the cosmological constant, and the Planck scale. So roughly the weak scale squared over the Planck scale is comparable to the cosmological constant. And these numbers are also relevant for dark matter. So when I said that you make the right amount of dark matter when it has weak scale interactions, is because roughly the energy density is set by Hubble at the weak scale, so v squared over m Planck. And so I don't want to enter too much into the details, but there are some anthropic arguments that leverage that. But they are a rare example, let's say, where dark matter would really be fundamentally changing the way we think about the hierarchy problems.
I mean, we have a problem with the cosmological constant,
Yes.
which is of the scale of 10 to the minus 2 electron volt rather than the Planck scale. However, presumably, dark matter contributes to the energy of the vacuum. Okay, so we cannot just separate the problems.
Sure, no, but yes, like but I mean, every other dark sector that you might have not discovered contributes to the energy of the vacuum. And I mean, I'm not trying to argue that the two problems are separate. I'm just telling you that the concrete ideas that we've had so far all worked in the opposite way. So we found a solution to the hierarchy problems, and that those contained a natural dark matter candidate. But I think it would be very interesting to reverse the perspective as you're proposing and see what happens. In concrete, we don't have a good explanation yet going in that direction.
In your, Philippe?
Yeah, so there was no history in your talk, so I just want to say a few words about the history of beyond the standard model in the lab. So obviously 60 years ago, there was no beyond the standard model, so there was nothing in the lab, but I think we should recognize the fact that Carlos, who sits in front of me, is the one who started beyond the standard model in the lab. I think Carlos arrived around 86, and for a long time he was alone almost in this lab doing beyond the standard model. And then gradually a bigger group appeared, and he's been growing ever since. So I think I just wanted to recall this fact that it was not in the 70s or in the 60s that this sort of physics, it gradually appeared in the lab. That's what I want to say.
Yeah, thanks. Indeed, I mean, as I said, I'm absolutely not qualified to recall the past, but indeed the lab has a glorious history also in this field.
Any more question or comments? So if there's no more questions, so let's thank Raffaele again.